So this video is going to talk a little bit more about the dot product. We've already discussed the dot product in general. We did it in the graphical form. Now we're going to do it specifically in the context of the Cartesian coordinate system and use some properties of those unit vectors that define that system to do dot products within vectors that are described in that system. So just to remind you, the dot product is an operation. It's a vector math operation that multiplies the parallel components of two vectors. So the dot product only multiplies parallel components. It doesn't multiply the full length of one vector times the full length of another vector. It only multiplies the parallel components. So previously we had always looked at like the vectors drawn as arrows. This was like the graphical representation. So in that case, you knew like the length of each arrow and you had an idea about the orientation of the angle between them. So in that case, we were just using this definition of the dot product that says the norm, the dot product between two vectors is the norm of the first vector times the norm of the second vector times the cosine of the angle between them when they are placed tail to tail. That's what we had been doing up until now. At this point though, now we've started describing our vectors in component form. So we're not drawing them anymore, we're describing them mathematically in a component form, which is like the sum of vector components. And so when you have your vectors like that, you don't necessarily know their norms right away. You don't know the angle between them just by looking, because you don't have a picture. All you have is like an equation. So like, let's say in this case, if I have vectors A and B, they're written in component form in this case. So vector A is here, it has some scalars times x hat plus a scalar times y hat plus a scalar times z hat. B is also written in component form. I don't honestly know what these vectors look like, but I can still find their dot product. At this point, we do something I call distributing the dot product. So you write like the component form of each vector and you dot them, which means you have to distribute the dot product between each of these terms. So you would do like the first term in that first set of parentheses dotted with the first term in the next set of parentheses. Then you would do that first term with the second term in the set of parentheses, and you distribute this dot product. So you actually, so in this case, I have two vectors that each have three vector components. When I dot these two vectors together, I'm actually going to get 9 different dot products just by like foiling or distributing this dot product between all of these terms. So I wrote out a few of these dot products, like these terms that come out from distributing the dot product. I really am just multiplying each term in the first set of parentheses by each term in the next set of parentheses, and you're adding all this up together. So you really should get 9 terms in the end if you're dealing with 2 3-dimensional vectors. So it can get pretty long and messy, but there will be some tricks that we're going to use because of the Cartesian coordinate system, the unit vectors in that system. We'll be able to simplify this a little bit, but that's what I mean when I say distribute the dot product. You'll do that whenever you have your vectors written in component form instead of graphical form. So to remind you some other uses, we're going to use the dot product over and over again, and I would say these are the 3 main uses of the dot product. The first one is to extract a scalar component of a vector in the direction of another vector. We use this definition to construct the component form of a vector. So this vector A dotted with x hat, that defines the scalar component of vector A in the x direction. So sometimes in problems, you'll be concerned about one particular direction at a time. So if you only want to focus on one direction at a time, you'll probably want to get the scalar component of a vector in that direction, and you'll use the dot product in order to extract that information. Another definition you've seen before, you haven't really used this one yet, it's the definition of the norm. The norm says that the norm of any vector is the square root of that vector dotted with itself. So now that you're going to get some vectors in component form, you can actually plug in the component form of that vector and then dot it with itself. So like in this case, if this vector A is 3x hat, let's say, plus 2y hat, you can actually write in the component form and then you'll distribute the dot product and actually calculate the norm of a vector. So this is something new that you probably haven't had too much experience with yet because we just haven't gotten to this point. Another use of the dot product is to figure out the angle between two vectors. So back to that general definitions of the dot product, if you can calculate the dot product of two vectors that were written in component form, distribute the dot product and figure out what the dot product is between those two vectors. You can also use the dot product to calculate the norm of each of those vectors. And with those pieces of information, now you can plug them into this generic definition and you can find the angle between those two vectors when they're drawn tail to tail. So you can kind of put everything together using the dot product, distributing it in component form, then using it to find norms, to calculate norms. If you know those things, then you can find the angle between these two vectors that were in the dot product. So now let's put it in the context, explicitly in the context of the Cartesian coordinate system. I just want to remind you just a couple things. Again, the definition of the dot product is the norm of the first vector times the norm of the second vector times the cosine of the angle between them. Also, in the Cartesian coordinate system, this system is defined by the unit vectors x, y, and z, x hat, y hat, z hat. They're defined by a right-hand rule. We talked about that. And something that's really important in this coordinate system is that each of those vectors is perpendicular to the other vectors. So x hat is perpendicular to y hat. That's perpendicular to z hat. All of them have 90-degree angles between those different unit vectors. Also remember, a unit vector has a norm of 1. Also, if you're ever doing a dot product between a vector with itself, any vector with itself has an angle of 0 with itself. It will be parallel to itself, and so the angle would be 0. So let's use all of these pieces of information that you've known for a long time, and let's put them into the context of the Cartesian coordinate system. So let's say if you want to find the dot product between x hat and y hat, let's use the definition of the dot product. It says that it's the norm of the first vector times the norm of the second vector times the cosine of the angle between them. X hat and y hat are perpendicular to each other, so I would plug in 90 right there. Cosine of 90 is 0. So we're going to plug in all these values. The norm of unit vector x hat is 1. The norm of unit vector y hat is 1. And then the cosine of 90 degrees is 0. So that whole thing becomes 0. So there's an interesting relationship here between all these dot products between the Cartesian unit vectors. They're all going to go to 0, all because they are perpendicular to each other. So I'm just going to kind of keep writing these out to really show you and to prove to you that the dot product between any of the Cartesian unit vectors has to be 0. And that's a big reason why we usually choose the Cartesian coordinate system, because it's convenient that the unit vectors that define that system are perpendicular to each other. Simple stuff like this pops out and we can use that to our advantage. One more thing that I want to talk about is just remember that any vector dotted with itself, you can also calculate that as well. So like x hat dotted with x hat is going to be the norm of x hat times the norm of x hat times the cosine of the angle between x hat and x hat. It's parallel to itself. So that angle in there is 0. The cosine of 0 is the number 1. So this dot product of x hat dotted with x hat is going to simplify to the number 1. Same thing with y hat dotted with y hat and z hat dotted with z hat. They are unit vectors. They're parallel to themselves. So that's why you can simplify those dot products to the number 1. So let's do a quick example here. I have vector h. I have an expression in component form for vector h, and we want to extract the scalar component of vector h in the z direction. So in your mind, you should be thinking to yourself right now, I need to do a dot product. The scalar component of vector h in the z direction is given by vector h dotted with z hat. So let's perform this dot product. So I'm going to copy down vector h. And now I'm going to distribute the dot product. I'm going to do that. I'm going to take that vector. I'm going to dot it with z. So I am going to, every single term in that expression for vector h gets dotted with z hat. All right, so I distributed my dot product. Now I can start using some of these simplifications that we just talked about for the Cartesian coordinate system. That first term, I see x hat dotted with z hat. That's going to be the number 1 times the number 1 times the cosine of 90. And that next term, I have y hat dotted with z hat. So again, that'll be the number 1 times the number 1 times the cosine of 90. And then in my last term, I have z hat dotted with itself. So that'll be the number 1 times the number 1 times the cosine of 0 in that case. And now we can make a couple more simplifications that this first term is going to go away to 0 because the cosine of 90 is 0. The next term is going to go away because, again, the cosine of 90 is 0. And so the only thing that remains is that last term, which all of that stuff is going to turn into, it's going to be 8.52 meters times 1 times 1 times 1. And so in the end, I just get negative 8.52 meters. So that's an example of using the dot product to extract a scalar component of a vector. And you might be saying to yourself right now, well, I could just look at this expression of h in component form. I don't need to do all that work doing a dot product to get that scalar component out. And I'm going to say, yes, you do. You are learners, you are beginners, you need to show all this work and really prove that you understand why we're doing a dot product, that type of thing. So at the moment right now, you might know the answer. I want you to show the work that proves that you know how to get this answer. This is a problem I'm going to make a separate video for. It's really using this dot product. We're actually going to use the dot product to do all of the things I said that it's going to be used for. So we're going to find some norms and we're going to calculate the angle between two vectors. So you can get started on this on your own, but I'm going to make a separate video just to show you guys exactly really how to get into a deep problem that uses the dot product in the Cartesian coordinate system.